So in this video, we are going to learn the steam engine. It's the first industrial application of the power engine that converting heat to work. The conversion of heat to work goes through the generation of steam. We burn coal, natural gas, or any combustible material. Sometimes we use nuclear energy to boil water at high pressures, and this boiled water drives a turbine. The turbine generates work, and now the lower pressure steam has to be condensed. As a result, discards its heat to the environment. We compress water, and then the cycle continues. So we're going to use the TS diagram represented here of water. And we are going to use the concept of power cycle here, and we will see a steam engine, how it works, and how we solve a steam engine problem, how we calculate the efficiency of the power conversion. So let's start. The steam engine starts by boiling water, but we have to boil water at high enough temperatures in order for our turbine to work, to deliver a sufficient amount of energy. Remember that the temperature difference between the hot and cold domains determine the overall efficiency of the cycle. So I'm going to discuss the Rankine cycle. All right, this is a particular cycle that is presently used in power conversion systems. So let's try to absorb heat from the environment. Our working fluid is water. So we're going to have a boiler. Into the boiler, we're going to receive high pressure liquid. We're going to receive water at high pressure. This high pressure liquid, which is here, is going to have a heat transfer process where it will first boil. On this side we have liquids. On that side we have vapor. Both are saturated. So we have subcooled water at high pressure is first heated up at constant pressure. Then it evaporates completely, still at constant pressure. Then it boils, and beyond this point, we have superheated steam. Beyond our saturation line, we have superheated steam, and the level of superheat determines how well we can convert heat to work. Now let's say that our system design allows us only to go that high in temperature, and this is our high pressure. So let me label this as T sub H. Here our system delivers, our boiler delivers the steam at this high pressure P and the temperature of T sub H, and this high pressure liquid is now being transferred to a turbine where we obtain work. And this is the work that we obtain from the turbine. For practical purposes, we assume that our turbine operates adiabatically. In other words, the heat exchange between the turbine and the environment is very small in comparison to the other sorts of energy exchange processes, especially those enthalpies coming in and going out, and the work that we obtain from this turbine. Now, this low quality steam at the exit of the turbine is taken and sent to the condenser. So, our system has received heat from the environment, delivered work. Now we're going to discard the heat to the environment, Q cold. At the exit of the condenser, we are going to have a low pressure water. And we're going to compress this water, but we're going to use a pump to carry out the compression process. Okay. So this is the flow chart of the Rankine cycle. Now let's see whether the components are well in place. We absorb heat from the environment at TH. Here our boiler operates at a variable temperature domain, but in principle we have a T hot, and in principle our boiler absorbs heat from the environment. We have shaft work obtained, but then we used some of it to drive the pump. That is why we call this work net. All right. Sum of the two is going to be our network. And we discard the excess heat to the environment. So this is our device operating in cycle, absorbing heat from the environment, delivering work, and discarding heat to the environment. Now we are going to place this on the TH diagram. So let me set states so that we can navigate between two diagrams. Here we are at state 1. High pressure water delivered from the pump is going to be boiled and superheat is added until we reach T sub H. Then we are going to, this process is at constant pressure. All right? The boiling process is conducted at constant pressure. Now let us see what the energy balance look like around the boiler. This whole process is a closed cycle. However, each and every process unit operates at steady state. So we're going to write our balance equations at steady state conditions. So when we take our energy balance, apply the conditions of being steady state, in the boiler, we don't have the du over dt term, the unsteady state component. We have a material steady state, and throughout this process, m dot is constant. a constant flow rate is being circulated throughout the system. The stream, there is only one stream that is coming in and one stream that is going out of the boiler. And the boiler only does heat exchange. So mdet times H in minus H out plus Q H is equal to 0. This is the energy balance for the boiler. Straightforward, as long as we know the state, temperature and pressure of the starting point and the finishing point, we can calculate the amount of heat that we can extract in the boiler from the environment. How are we going to know those temperatures and pressures? That is the part of the training of the engineering, that the boilers are designed relative to the available turbines, and boilers are designed relative to the fuel that is going to be used. And of course, we have to pay attention to the material of construction as well. So typical temperatures are around 700 to 800 degrees Celsius. Typical pressures are 5 to 10 megapascal. They are not trivial, but those are typical numbers. But each and every cycle, of course, requires its own design constraints and design parameters. So from those rules of thumb of typical temperatures and typical pressures, we actually set ourselves in a coordinate location in the temperature entropy diagram of steam. And this diagram is going to be very useful when we are designing this whole Rankine cycle. All right, we have done the balance for the boiler. Now let us write the balance for the turbine. Again, turbine is operating at steady state. Mass flow rate is constant. I am going to also use the indexes as the state numbering. So instead of in and out, I will say 1, 2, 3, 4. The inlet to boiler is H1 and outlet of the boiler is H2. Now for the turbine, at the inlet, my enthalpy is H2. And at the outlet, my enthalpy is H3. And I get the turbine work, and the net balance is 0. So the net work that I obtain from the turbine is equal to the difference of the enthalpy of the incoming steam and outgoing steam. Now I know the initial condition. Now this is my turbine design, right? I have selected my temperature, I have selected my pressure, but I don't know the exit condition. But remember, when I was drawing the flow chart, I mentioned one thing, that for all practical purposes, I said that our turbines operate adiabatically. Now, the limiting condition of the turbine would be a reversible operation. Limiting in what way? Limiting in the performance way, that everything is working so perfectly that our turbine is operating reversibly. Now, when I say that the turbine is operating adiabatically and it is operating reversibly, it should ring a bell, because we have learned from the entropy balance that if a process is adiabatic and reversible, then the entropy remains constant. So let's apply the entropy balance around the turbine. So again, steady state condition prevails throughout the system, including the entropy balance. So the term on the left-hand side of the equation is 0. Our mass flow rate is constant, and for the turbine, inlet entropy is S2 with a hat, outlet entropy is S3 with a hat. Entropy generation is 0. There is no heat exchange. Q is 0, S generation is 0. As a result, we observe that S2 is equal to S3. And this fact makes us realize why we have this temperature entropy diagram. So for the turbine, now this line going all the way up belonged to the boiler for a constant pressure operation. Now I'm going to have a vertical line representing my turbine, which is operating at constant entropy, right? I will go as low in pressure as possible, but I will not go way below the atmospheric pressure. It is going to create other problems. So I will remain within the reaches of atmospheric pressure. I can go slightly lower for some other technical practical purposes, which we may discuss later on, but this pressure is somewhere around atmospheric pressure. So I arrived at the saturation curve. Sometimes I can go just a little bit below saturation curve, but not too much. Let's remain around saturation line. So this is our point 3. Now the fact that I know the entropy of my point 3, and I know the fact that I'm going to be very close to the saturation line, allowed me to specify the state of the system at point 3. I know everything. I can find the enthalpy, and I can calculate the turbine work. All right? How about the condenser? Okay, between point 3 and point 4, I'm going to have a very similar energy balance to the boiler. Let me write. For the condenser, my energy balance is m dot H3 minus H4 in minus out plus Q sub C is equal to 0. I know the inlet, constant entropy. In the condenser, all I have to do is to condense water I don't need to do anything further than that. Just simple condensation. This process is a constant pressure process. So let's label the processes with their state variables also afterwards. And it's going to take us from point 3 to point 4. And I know my point 4. I know the pressure that I have started with. I will end up at the same pressure, and I will be on the liquid, saturated liquid line on the temperature entropy diagram. So I know the state. I know all the variables. I can calculate condensation heat. There's one more process unit that I have to deal with. It is the pump. Again, I have a very similar energy balance. H4 is the inlet. H1 is the exit. And this is, again, 0. I no H1. It is my starting point. All right. Let me write the entropy balance around the pump also. It's operating at steady state. Entropy enters at state 4, leaves at state 1. Again, for the practical purposes, that our pump operates adiabatically, and for practical purposes, our pump operates reversibly. No entropy generation, no entropy due to Q over T term. As a result, my pump is operating also at constant entropy, similar to my turbine. S4 is equal to S1. All right? In fact, this is how I know S1, not the other way around. Starting from an atmospheric pressure liquid, I will use a pump that is going to operate at constant entropy, and it will bring the liquid to the pressure that I will run my boiler. All right? So this is how the states are identified. All right. Now I know all the states. I know my state variables. I have my energy balance equation. Right now I don't have my steam table or the TS diagram to number these processes, but I strongly recommend that using the TS diagram of water, of steam, design yourself Rankine cycles, choose your temperatures, choose your pressures, and evaluate the energy balance for each process unit until when? Until we're going to calculate the efficiency of this cycle. Now let's remember, what was the efficiency of a power cycle? Efficiency of a power cycle was minus net work divided by QH. Net work is equal to turbine work and the pump work summed up. One is going to be positive, the other one is going to be negative, and the net work is going to be the sum of that divided by Q sub H multiplied by 100. So this is the efficiency of percent efficiency of a Rankine cycle of the steam engine. It is still in practical use. We are using this to generate electricity. Sometimes still some of the transportation units, mostly historical steam engines, are run on the railroads. They drive ships, but mostly the steam engine is limited to power generation, generating electricity. This turbine is used to generate electricity. Now let's just relax some of our assumptions and start to ask the question, what if our turbine is not operating reversibly? If it is not operating reversibly, it should generate entropy and it should exchange heat with its environment. All right? So the fact that the turbine is not operating reversibly is going to change the game. We are going to end up at a point of 3 prime. That is not going to be equal to 3, but it is going to have an entropy, be very careful, an entropy that is going to be greater than the entropy at point 2. So our process is not going to be a straight vertical line. Our process is going to have some entropy generated, and it is going to be little bit far away. But make sure to understand that our condenser is going to operate at constant pressure. All right, we are not going to make any changes in pressure between the turbine and the condenser. As a result, we have to find the isobar, and we have to find the point where our irreversibilities are taken into consideration. All right, so this yellow line is for the reversible turbine, reversible operation of the turbine, and the pink line is where we have irreversibilities. All right, and the way we treat those irreversibilities could be top-down or bottom-up. Top-down means that if we have a heat loss of so and so many kilojoules, how much would that translate to in terms of entropy generation using the entropy balance? Or it would be a bottom-up, that during the operation we measure the conditions and we determine the heat loss from the state variables. Now, the other thing that is useful to learn is to just find ways of increasing the efficiency of your cycle. The efficiency of your cycle depends on the amount of work that you obtain from the turbine, and you can maximize this by gradually adding heat to your turbine. Now, your steam entering at state 2 in this diagram may expand a little bit, and then we can take this steam, perform a heat exchange, and deliver it to the same point. In other words, we can just have a constant pressure heat addition to the turbine, which expands, and then we take and add some more heat, and so on and so forth. As such, if we can achieve some more work, look what we have done. We have expanded the area covered by the frame that surrounds our cycle. Actually, this frame that surrounds our cycle, the area of that frame is a simple multiplication of temperature and entropy, or it is integral T ds. That corresponds to the net heat exchanged in this power cycle, and that's equal to minus net work of this power cycle. By adding heat in the turbine, we have expanded the area, we have expanded the network, we have increased the efficiency of the turbine.